Hello, everyone. We're just now letting folks into our webinar. We'll give people just a few more minutes to join, but thank you for being with us. Merry Christmas and Happy Holidays. I know we still have some gift shopping to do, so hopefully after today's webinar, it'll be time to get out and enjoy your weekend and get ready for the holidays. So again, we'll just wait for another minute or two, and then we'll get started. We have a very wide audience today. We've got people from all over the world in Asia, Japan, and China, and then in Europe. We have a few colleagues from Russia with us and from South America. So very much appreciate all of you being with us today, and I'm sure you'll learn a lot from today's great presentation. All right, well, why don't we go ahead and get started? Again, thank you for being here from wherever you are. Good morning, good afternoon, good evening. And some of you are late at night, so we appreciate you being here. My name is Dave Cadu, and I'm honored to be the CEO of IWCS, and I will be your moderator today. A few housekeeping items. Please note that as an attendee, you're part of a larger audience. So during the presentation, all participants will be in listen-only mode. And also as a reminder, this event is being recorded for rebroadcast. So we will be posting this webinar on our website for you to go back and watch again or share with your colleagues. We encourage you to submit written questions at any time during the presentation. Please use the chat panel at the right of your screen. After typing in your questions in the chat, in the space at the bottom, hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. So find the chat, and that's where you'll enter your questions. Our IWCS webinar series event today is hosted by the Cable and Connectivity Industry Forum. We're excited to be preparing for next year's conference in Providence, Rhode Island. So think about submitting an abstract. We'll talk more about that later. Today, we welcome Jairo Stocco, the applications engineer for the European, Middle East, and African region, the optical fiber division for Corning Optical Communications. He is from or a resident of North Wales in the United Kingdom. Jairo will be presenting his paper today on the high-density optical cable with ultra-low loss, large effective area using the International Telecommunication Union standardization sector, the G.654.E Optical fiber. Jairo joined Corning in 2018 and is responsible for technical support for optical fiber customers and end users within the Europe, Middle East, and African region. Jairo graduated with a bachelor's degree of radio and television from Methodist University, and also a bachelor's degree in telecommunications engineering at the Salesian University, both of which were in Brazil. Currently, Jairo is a Global Master of Business Administration candidate, an MBA at the Manchester University in the UK. Jairo has focused his career on many areas of telecommunications, working with radio frequency identification, unified communications, and optical fibers. So thank you, Jairo, for being with us and to present your excellent paper. So carry on.
All right. Okay. Well, thank you very much, David, for the introduction. Thank you very much for the invitation for this presentation as well. So as David said, my name is Jerry Stolko. I'm working on Corning as an application engineer for optical fibers in Europe, Middle East, and Africa, the EMEA region. I would like to thank you, everyone was able today to join this section. It's really a pleasure to be here representing my company, Corning, and my colleagues, of course, who supported the creation of this article, who were Ian Davis, who is the application engineer manager on EMEA area, Lydia Galdino, who is assistant engineering manager on Corning as well, and also Gianni Maiorani, who is in an audience today. It's the technology manager at Ecotel, our customer that supported the creation of this paper. On this paper, we are going to talk about the high-density optical cable using the G.654.E TXF fiber, understand some points of attention of the manufacturing process. We're going to talk a little bit about some details of the optical capabilities of this cable and also the bandwidth performance of the cable too. I'm sharing two screens here. Let me see. Yeah, it's all good. So setting the scene and introducing the motivation for the creation of this article. Some years ago, we all lived throughout the COVID-19, and this time showed us, for only for us, but for the entire world, how dependent we all are from the telecommunication infrastructure, and we never, in all the human history, created and transmitted so much data like we are doing within the last years. The inspiration for this cable that we'll talk about today came from a customer that, like many others around the world, was being challenged to improve the capacity of their backbone to get more bandwidth, achieve higher bandwidth capacity, to comply with this increasing demand on data that we are all seeing, and also to find solutions for cables that could reach longer distance compared to the cables that we already had in the past. But doing this, of course, without breaking the bank. That's an important requirement. So the interesting thing about this article that we created is that these requirements that the end customers presented to our customer, which is Ecotel, and Ecotel, of course, brought to us, were not something exclusive for this specific customer. Those demands are actually a trend in the industry, especially for this type of specific of customer that demands this kind of things we're going to talk here during this presentation. And of course, for long haul and data center interconnection networks. Those requirements that we're going to talk now are requirements that I call the requirements for future proof networks. Let me see. Yeah, it's moving now. So the first requirement for this future networks that I'm talking about is increased bandwidth. We have a lot of new technology emerging, each of them with own acronyms, and there are a lot of acronyms around. To give some examples, we have the 5G rollout that will require a lot of fibers in the backbone to support it. The IoT or Internet of Things, and the millions of devices that are daily being connected to the networks. Virtual reality, which is becoming a trend more and more recently. AI, artificial intelligence, we are really trending currently and requires an incredible amount of processing power and interconnections between the data centers. All of them are very data hungry. All of these applications, they need a lot of data, they demand a lot of bandwidth, and this is a challenge that need to be faced. The modern networks also need to be cost effective, because planning and building infrastructure is expensive. So when our customers, actually when the end customers build it, they wanted to build it right, and they wanted to build just for once. They do not to need to come with future upgrades, install more cables in spaces that are already jammed. So they need to build it once and just for one time to increase their network capacity. As you know, there are different types of networks. We have local networks, we have metro, long haul, submarine, different types of networks. But this cable that we're going to talk about today and the fiber that this cable is using is focused on the long distance reach networks. And our customers want these networks to reach the longest distance as possible, but also being fast, being highly capable in terms of high data rate that is demanded. But this can be sometimes particularly challenging on this long haul networks, the long distance, because of some technical reasons that we're going to talk within the next minutes. And then based on these needs that we're talking, the desires of their customers for these future networks, the challenge for the cablers and for the network operators is how to design a cable that can achieve high capacity over this longer distance that we mentioned, but doing it with a low cost per bit. This is the challenge. But of course, adding to that, there is a new important challenge as well, which is rising within the last years, which we can see that affect more some countries than others, but in a higher or lower degree affect all of them, all of the customers, which is to find a way to increase the capacity and the bandwidth of the cables, but overcome the space constriction, which is already affecting many of our customers in many different countries. They want cables that can transmit more data, but they also need to reduce the size of these cables because the space available to install them is getting smaller and smaller. It's getting too crowded, or even with right of use issues in some cases that would not allow future improvements. So they need to install it and install it once. Did they change the slides? Yeah. So in summary, there are many demands, many desires or requests for the customers that need to be fulfilled, and not always these demands are aligned. Many times there are conflicting between each other and representing forces on like opposite directions. But in the end, all of them need to be addressed on the best way as possible by the fiber and cable manufacturers. So the solution engineered by Corning and Ecotel to support these demands was this high density loose tube micro cable, which has a diameter of 7.6 millimeters, contains 6 tubes, being 2 of them used only with fillers, which was absolutely a project choice. They could, of course, contain fibers if the customer requires, but in this case, they were 2 of these tubes were only fillers. On the remaining 4 tubes, we have a total of 96 fibers, meaning that each tube contains 24 fibers. 12 of them colored only, and 12 of them colored plus with 1 black ring mark to be used to differentiate then the fibers with the same color. Just a second, please. I'm sorry, but my voice is not very good within the last days, so we need to have some water during the presentation. So the fiber chosen to be used in this cable was the Corning TXF fiber, which is a G.654.E standard fiber that contains some interesting characteristics that make it great for long-haul networks, which we will talk about during the presentation. But for now, as we're talking about the cable manufacturing process, there are 2 important characteristics that to be mentioned at first, which are the effective area of this fiber, which is 125 micron square on the TXF fiber, which is much larger when we compare it to a standard G.652.D fiber, which contains 83 micron square. And will be the comparison baseline today. We're going to compare a lot of the TXF, which is the G.654.E, with the G.652.D fiber. So it's going to be our comparison baseline. Another characteristic interesting to mention is the macro band requirements of both fibers. As we can see on the ITU-T tables on this slide, because the G.654.E standards feature the same macro banding requirements of the G.652.D, in which means that the TXF fiber will should behave in the same way when we cable both fibers, the G.652.D and the G.654.E. They should behave kind of the same way on terrestrial networks. Said that, some of the attention points during the manufacturing that probably worth mentioning, and that could cause micro and or macro bending issues if not performed properly, are related first to the ring marking. As you know, using more than 12 fibers in a tube requires some kind of method to differentiate the same colors within the tube. And considering that the cable uses a fiber with larger effective area, and the whole extension of the cable, it's a long cable, and the whole extension will be ring marked. If this process is done in a non-uniform way, this could lead to some attenuation buildup. So a proper attention on the amount of ink applied during the coloring and during the ring marking as well, for the ink mixing after the coloring as well, when we are curing the fiber, the curing process. Attention to all of these points is always recommended for color, and especially for colored and ring marked fibers, because this can be a source of attenuation, especially in these long networks. Another aspect that needs to be well controlled is the extrusion process. It's important to make sure that the correct amount of gel, powder, or whatever water blocking is being used in the cable is done, because a proper control of this parameter and of the extrusion itself is quite important to avoid sources of macro bending inside of the cable and defects in the walls of the cable that could affect the fiber performance and cause macro bends and consequently attenuation on the cable. Speaking on the manufacturing process control, the use of the right and well-controlled parameters also pass through this use of a proper excess fiber length, EFL, because this is the way that the cablers can do to avoid the fiber to become buckled inside of the cable if you apply excessive length, or even compressed inside of the cable, which can happen because of temperature variations, cable loading during the installation, or during the normal lifespan of the cable too. So that's important. That's important to take into consideration. The same attention was applied to make sure that an adequate and well-controlled lay length was used by Ecotel when they were manufacturing the cable, which helps to avoid the tubes and consequently the fiber which is inside to get flattened inside of the cable, which could lead to higher than expected attenuation on the final cable. The goal here is not like give too much instruction of cabling, of course, but it's just some points of attention that Ecotel needed to be paying attention in the cable, and the cablers need to pay attention when they're manufacturing the cable to make sure they're going to have the best results at the end. The results obtained during the tests made by Ecotel, and which were afterwards confirmed during the commercial manufacturing process, were very interesting, as the attenuation introduced by the cabling process, the whole cabling process, which involved coloring, remarking, buffering, and at the end the cabling itself, were quite good, with low attenuation increase when we compare the bare fiber attenuation distribution to the cabled attenuation distribution. The bare fiber median attenuation was 0.166 dB per kilometer, and we got a final cabled median attenuation of 0.168 dB per kilometer after some dwell time when the fiber relaxed a little bit. We can, of course, see some outliers, but they are normal and represent like a very small portion of the results, and were considered normal for this type of cable and this manufacturing process, considered totally normal. To conclude this introduction about the manufacturing process, the fiber went through the remaining standard tests for cables, which are tensile tests, crush and impact, repeated bending, and of course, in the end, to conclude, one of the most important for me, which is the temperature cycling test, which shows that the cable can behave well on temperatures between minus 30 degrees and plus 60 degrees Celsius. And it helps to show the resilience of the cable to be installed in very tough environments during the lifespan. Now, moving to the characteristics of the fiber that we use in the cable, leaving a little bit the manufacturing side and moving to the characteristic of the fiber itself, and why we thought that this fiber would be a good choice for this cable. Starting with a quick introduction about the fiber itself, and then we will move to the simulation results. There are two main aspects, I would say, that I wanted to mention here. The first one was actually already mentioned slightly before, which is the large effective area of the fiber. Comparing the G.654.E fiber, TXF fiber, that we used with the G.652.D fiber, the 125 micron square area of the TXF fiber allows 50% more power to be pumped in the fiber in a manner that would not be possible to do using a G.652.D fiber, because pumping more light in a smaller effective area could cause some non-linear effects. I don't know, four-wave mixing, self-wave modulation, cross-phase modulation, just to mention some. And these effects would compromise the accuracy of the signal detection when we receive the signal at the receiver. We will cause the data to be lost and then the bandwidth to be compromised. With this larger effective area, these problems can be controlled, and we can pump more light. It means that the light can travel further down the fiber, increasing in the end the OSNR, which the optical to signal noise ratio, or the proportion of the signal compared to the inherent noise of the fiber, and consequently increasing the distance that the link could achieve. Another aspect important of this fiber that I think is worth mentioning is the ultra low loss that the fiber features, which is around 0.166 dB per kilometer typically, which allows, again, the signal to travel further down the fiber as we have less optical power lost during the intrinsic glass attenuation, which is normal of the fiber. As we will see in the equation in the next slide, the attenuation is indirectly proportional to the SNR. And that's why a low attenuation fiber can help to increase the cable capacity. We're going to talk more about this when we see the equation. Two things that I think it worth mentioning as well. For coherent networks, a slightly higher dispersion would also help to reduce the nonlinear effects caused for this signal mixing, because it helps to spread the signal on the fiber to avoid the penalties that I already mentioned. So I think this is something that's worth mentioning, in which the TXF features this slightly elevated dispersion. And also the 1520 nanometers cutoff wavelength of this fiber, which allow the operation in the window of optimum or lowest attenuation of the fiber. So I think it's worth mentioning too. These characteristics makes the TXF a great fiber for these long haul networks with longer spans, and that will be part of a metropolitan network, for example, just to mention one. The fundamental limits of an optical communication system and how it will perform are determined by the combination of the noise from the transceiver and from the optical amplifiers, plus the optical fiber nonlinear distortion, which is inherent to the transmission through silica fiber. We cannot avoid that. Plus the number of spans, which will limit the reach of the system. To demonstrate the cable capabilities, I had the great support of my colleague Lydia to simulate a system using the parameters of the cable and the fiber and compare the performance of this cable that we are studying, which is using a G.654.E fiber, and a theoretical cable which would contain G.652.D fiber instead G.654.E. And then we could compare what would be the cable capability in terms of bandwidth of both cables and see the advantage of the cable we are testing. To start the simulation, we analyzed all the components that would affect the cable capacity using this equation on the slide, which states that the optical signal noise ratio, or linear OSNR, the linear part of SNR, is equal to the power per channel, which increases with the effective area of the fiber as we launch more power, divided by the span loss, which is determined or affected by the fiber attenuation, multiplied by a component related to the Planck constant, which is the pph on the equation, which is a basic physics constant, multiplied by the amplifier noise figure, which is NF, which is the representation of the amount of noise generated by the amplifier, and the number of fiber spans, which is the N on the equation. So the equation is a representation of total signal power launched in the fiber, which is trying to balance itself with all the other components that are pulling to the opposite direction, as the image represents. And higher is the result, or higher is the OSNR, longer will be the reach of the link, and better will be the detection capacity of the receiver at the end of the system without losing data. Talking about the simulation details now. This simulation used a basic Gaussian noise model, which is similar to the one showed on the previous slide, but that was used to calculate the received signal-to-noise ratio after the coherent detection and the electronic dispersion compensation. Some of the details of the parameters used here in the simulation are in the slide. I will not go into details into this, but you can see here on the left side. And based on this simulation made by Lydia, we could get some interesting information. And this first chart starts showing this, as it shows the comparison between the optimal launch power that will need to be used in the system to allow us to achieve the highest possible SNR performance. As we know, the silica fiber has a nonlinear response to higher power spectral density inside of the core, which means that contrary to linear systems, it doesn't matter if I launch more power in the core. The SNR will not simply increase with more power. There is this function that will define the optimal point based on the power launched. The results for the G652D fiber here are in the red line, as you can see. For the G654.E fiber is in the blue line. On the linear regime, which is everything below 0 dBm, the G654 fiber has a higher SNR total, mainly because of the lower attenuation of the fiber. When we move to the right side of the chart, on the nonlinear threshold, we also see the advantages of the bigger effective area of the TXF fiber, the G654E, translated in an improved SNR under a higher power regime. While the optimal launch power for the G652D fiber is around 3 dBm, as you can see, to achieve a SNR total of 13.80 dB, the optimal launch power for the G654E fiber, which has a larger effective area, is naturally higher, allowing a power launch of 4 dBm, which will yield a SNR total of 15.26 dB, which makes in the end a difference of 1.46 dB between both fibers at the optimum point. In practical terms, it means that with the TXF fiber, you could achieve the same SNR than the G652D, but with less power launch. That we will see in the practical terms. Note that this extra SNR that we can see here is not extra optical budget. That's only the difference of the total signal-to-noise ratio at the optimal point between these two fibers, which is the combination of the three components that affect them, which is the amplifier noise, the silica fiber natural noise, and also the noise generated by the transponders. So that's the combination. And this is a kind of a straightaway manner to see how the TXF fiber allow higher power and how it translated in better SNR on the link. If you wanted to see how this translates in better optical budget, then we will need to see the next chart, which is this one, because this chart used the SNR data that we calculated and converted in optical to signal noise ratio, applied to the distance of the link on the simulation, of course. In this situation, we can see that the G654E fiber allows around 3 dB of extra optical budget throughout this whole 4,000 kilometers link of the simulation, quite constantly between the beginning and the end. And this could be translated in different benefits to the operators that will use this fiber, this cable. From extended lifespan for the cable, because you have more optical budget to more maintenance, to more splices. Also extra reach of the cable, can go further distance, more bandwidth available, just to mention some of the benefits that the operators would have because of using this fiber. Just a second. Sorry. So yeah, the next step of the simulation will be then calculating the signal-to-noise ratio after the coherent detection to understand what's the advantage that this extra SNR could give us in terms of distance, which when using the G.654.E fiber, which is the point that we wanted to reach here. As we can see in the chart, the SNR total after a link of approximately 500 kilometers was around 15.57 dB for the G.652.D fiber, which is in red, and 16.52 dB for the G.654.E fiber, which is in blue, which represents a delta of approximately 1 dB. While the link distance gets longer, we can also see this delta growing between the two fibers until we finally reach the theoretical 4,000 kilometers link. And at this point, the delta of the SNR between the two fibers will reach its maximum, which will be 2.3 dB, giving us some important extra optical budget, even after this long link, which again could be used for maintenance purposes and the others that I already mentioned. Something that we did here in this article that we thought was interesting is that we left the word of the dBs, and we also talked a little bit in the word of data transmitted, where we measure the capacity of the cable of the fiber in terabits per second in terms of the fiber, or petabits per second in terms of the whole cable capacity. Here we can see that the fiber capacity in terms of terabits per second, as I mentioned, is plotted against the distance reached for use on the C-band. And then we can compare this with the G.652.D, which is again in red, and the G.654.E in blue. On a shorter 500 kilometer link, the G.652.D have quite a good performance, reaching 40.4 terabits per second per fiber, but it's of course outperformed by the G.654.E fiber, which reached 43.3 terabits per second, which is 2.9 terabits per second more per fiber. But in the long distance that we see the G.654.E fiber standing out because it can keep a capacity of 29.7 terabits per second against 23.5 terabits per second of the G.652.D in this 4,000 kilometer links, representing over 20% more data per fiber in the long link. So if we transport this difference of each fiber to the whole cable, to see the whole cable capacity, we will be able to observe a huge difference between both fibers. In terms of capacity versus distance, this chart tells us, for example, that you can have a 4,000 kilometer link using the G.654.E fiber, and the capacity would still be the same of a 2,000 kilometer link using the G.652.D fiber. That's the double of the distance, but still keeping the same capacity of the cable. Another interesting way to see it now in terms of data capacity is noting that on this 4,000 kilometer link, the cable using the G.654.E fiber gives us 593 terabits per second of total extra capacity. That's extra capacity, or 297 terabits per second on each direction. And this using as a reference the capacity of the G.652.D fiber at the end of the 4,000 kilometers, just for a comparison by baseline. It means that using the G.654.E in this cable brought us an advantage equivalent to 14 extra G.652.D fibers in the cable. As a comparison, it will be like instead the cable having 96 G.654.E fibers, like it has now 110 G.652.D fibers to be comparable to the same fiber, the G.654.E fiber, which is a considerable difference in terms of capacity and cost of operation, cost of equipment to manufacture the cable, space of the cable. It's a considerable difference that can be taken into account when we are building the network. All these characteristics that I've been mentioning during this presentation make this TXF fiber capable of keeping transmitting the maximum capacity of the transponder data rates to distance longer than the G.652.D fiber could do. There are plenty of papers that shows some simulations for long links for similar or even different applications. We even refer some of them on our article. If someone is interested to check the article, I'm not sure if I think it's available on IWCS website, but if not, Corning will make the article available on our own website. So yeah, you can check. There are plenty of articles that were referenced there. But the point is that, as you can see here in this slide, for links around 1,000 kilometers average, this fiber can keep a channel data rate of 800 G. And for much longer distance, like this 4,000 kilometers link that we use on our simulation, 75% of the maximum transponder data rate capacity is still being transmitted and being kept up for the fiber, showing that the great performance of this fiber for these long hauls that we mentioned at the beginning. So to conclude, this main application of this cable manufacturer in partnership between Corning and Ecotel is long-haul networks using for longer spans that can, in this case, that the cable can use the benefits of this high-density terrestrial micro cable, especially in environments where the duct spaces are crowded. The spaces for new cables is limited. That's where you can use this cable and develop new cables using this fiber. The TXF is a good fiber choice because, as I said, enables a high capacity, ultra low attenuation, large effective area, and make it a really great choice for interconnect data centers, these metropolitan regions that need to be interconnected, and there's backbones that require this type of fiber. The lower attenuation and the large effective area of this specific fiber allows the use it on longer spans. You can use fewer amplification sites because of it. In this case, you're gonna have the amplified spontaneous emission noise reduced, and because of that, you're gonna improve the signal to noise ratio. I guess that's it. I'll open for questions in a minute, but before, I just would like to make a quick special thanks to IWCS for the invitation to present on this webinar. It was a pleasure to present in the conference, in the webinar. I hope I can see some colleagues in the next year there. It was a great opportunity for network, to gain some knowledge. Also, a big thank you for for my colleagues that helped on the construction of this paper, starting with Gianni Maiorani, who is the technology manager of Ecotel, one of our greatest partners here in Corning, in which embarked on the idea of supporting this paper. A special thank as well for my manager, Ian Davids, 35 plus years of experience on optical fiber, one of the great references in the industry, and a great reference for me as well. And for last but not least, a big thank you to my fellow Brazilian colleague, Lydia Galdino, which helped with the simulations and also helped proving every day that there's a lot of great minds coming from Brazil. Well, also thank you everyone that connected today. So now I would like to give the word for David again and open for questions.
Jairo, that again, fantastic presentation. A lot of information there on obviously the design, the capabilities, the manufacturing, very comprehensive. And we thank you, and we look forward to your future contributions at IWCS. If there are any questions for Jairo, please enter them in the chat. One question was in the manufacturing process, you mentioned the lay lengths and the requirements. Is there an optimum lay length to minimize attenuation, and how do you control that? Are they consistent, or can you describe that a little bit more?
It's a good question. There is also an optimal parameter for the cable, but the point is, it's gonna depend of the cable design. That's important to mention, because each cable design requires a specificity on this parameter. So yes, there are optimal parameters. We can help with that for our customers. We are always in contact with them to help with that. So I cannot tell you now like a ballpark for which is the best one, but it needs to be really paying attention, because it's one of the most important parameters on fiber manufacturing, fiber and cable manufacturing. Unfortunately, I cannot give a number specifically, but yes, there are. We cannot be too much, but not too low. So we need to see case by case.
Good, thank you. Due to its larger mode field diameter, does this fiber fiber less sensitive to connector mating misalignment?
Connector misalignment.
Yes, is it more sensitive, due to the larger field the diameter?
I wouldn't say for connectors, no. One thing that's important to be taken care of is splicing, because when you splice fibers with different mode field diameters, with a higher and a smaller mode field diameter, then you can have some difference of attenuation that you could see on the OTDR as gainers or losers. So for connectors, I would not say that there is a big difference, because at least here I never experienced any big difference. More for splices, I would say.
Yeah. Any more questions from the audience? We have just a minute or two more. I don't see any more in the chat. Again, it was a very comprehensive and well presented paper. Again, if you wish to view the presentation again, it will be recorded and put on the IWCS website. So seeing no more questions in the chat. Again, we want to thank Jairo for presenting today. You can see, if you want to reach out to Jairo, you can contact him at his email. You should be able to see that on your screen right at the moment. Let me enhance that. There you go.
Yeah, please feel free to reach out if you want on my mail, LinkedIn. I'm always happy to connect with colleagues and networking. It's always great. So please feel free to reach if necessary.
That's fantastic, and appreciate that. And I'm sure our audience again will be interested to contact you. Each of these IWCS webinar events are recorded, and like I mentioned, will be archived on the IWCS website. It'll take just a few days to get that posted. So please feel free to go to our website. You can see this webinar as well as many others on a variety of topics. These are the outstanding presentations from our previous conferences. The IWCS webinar series will conduct technical presentation webinars each month. Typically, we schedule these on the third Friday of each month. We also have several sponsored company events as well to spotlight products and applications. Our next scheduled technical paper webinar will be on January the 19th, and I can't believe we're saying 2024 already, but that will be the next technical paper webinar. Each of you will be receiving an announcement for that event, so please feel free to share our announcements with your colleagues so that they can join in as well. Before we conclude, I don't see any more questions. Becky, do you see any more questions?
No, I do not.
Don't think so. Okay, very good. Okay, it's important that we all recognize and thank our IWCS partner sponsors, including Corning, who contribute greatly to the success of the Cable and Connectivity Industry Forum, both in terms of technical content, as you viewed today, as well as their strong leadership and generosity. If we did not have their support, we would not be able to bring these important technical innovations and information to you and our global community. So again, we thank Corning and these other leading suppliers in our industry for their outstanding support. Want to make sure that you are aware that our conference is approaching in 2024, and we're in the process now of establishing the program, the most important part of which is you and not only your participation, but if you can kindly consider presenting a paper on behalf of your company and your outstanding work that you do. Like today, there can be some outstanding recognition and exposure for your efforts at IWCS. Our call for papers is now open, and we hope that you'll think about presenting. The abstracts can be submitted from now and through the first part of April, and then we'll develop our program accordingly. So for over 72 years, IWCS has been the recognized leader to showcase these new technologies in cable and connectivity for products and processing and applications. And again, I'll remind you that our next conference is going to be in October in Providence, Rhode Island, Monday through Thursday, October 14th through the 17th. And so please watch your inbox and social media, as well as our website, to learn more as the exciting information becomes available. Again, it's very easy to get this information on our website, as well as to submit an abstract. So we hope that you will do that. More than anything else, we wish you a healthy and joyous holiday season with your family and loved ones, and we look forward to being with you again in the new year. So enjoy your time with your family, and thank you for being with us. Have a great weekend. All the very best. Take care.